Consider the function ln x. How can we find a power series representation of ln x? In order to do this, we need to realize that the integral of 1 over x dx is the natural log of x plus c. And so we need to write a power series representation of 1 over x. So let's do that. So we need to put it in this form: a over 1 minus r, the sum of an infinite geometric series. So starting with 1 over x, how can we do that? What we need to do is add 1 and negative 1 to the denominator of the fraction, because x plus 1 minus 1 is still equal to x. The value is still the same. Now I'm going to take this one and move it to the left side because we need it there. So I have 1 plus x minus 1. Now we need to change the positive sign to a negative sign. So to do that, we're going to factor out negative 1 from x minus 1. So it's going to be 1 minus, and then the positive x is going to change to negative x. Negative 1 is going to change to positive 1. So now it's in this form. So we can clearly see that a is equal to 1 and r is negative x plus 1. So let's start with the geometric series a times r to the n. And let's represent it as a power series. So this is going to be 1 times negative x plus 1 to the n power. Now, this particular power series is not centered at 0, and we need to put it in this form. That is x minus c to the n. So this is going to be, in order to do that, we need to take out a negative 1. So if we pull out a negative 1 from negative x plus 1, it's going to be positive x minus 1 to the n power. Now we need to distribute the exponent to negative 1 and to x minus 1. So now this is going to be negative 1 to the n times x minus 1 to the n. At this point, we can make the statement that 1 over x can be represented by the series from 0 to infinity of negative 1 to the n times x minus 1 to the n. So continuing from this expression, we could say that the integral of this series has to equal the natural log of x plus the constant of integration, capital C. So how can we find the integral of this expression? Keep in mind, n is the constant, x is the variable. So we need to rewrite the constant first. That's going to be negative 1 to the n. And then we need to use the power rule on x minus 1 to the n power. So we're going to add 1 to the exponent. N becomes n plus 1. And then whatever this is, divide by that result. So this is going to be equal to ln x plus c. Now the next thing we need to do is calculate the value of c. So what is c equal to? How can we find it? What we need to do is plug in some value into this expression. So what value of x will be convenient to use? So if x is equal to 1, then this entire expression becomes 0. 1 minus 1 raised to the n plus 1, that's 0 to the n plus 1, and 0 times anything is 0. And so this is going to be 0, which equals ln 1 plus c, if x is 1. Now the natural log of 1 is 0. So we have 0 is equal to 0 plus c. Therefore, the constant of integration is just 0. So we can get rid of this. And let's not forget to write this sigma notation. So therefore, the power series representation for the natural log of x is what you see here, highlighted in red. Now what about the radius of convergence and the interval of convergence. How can we find that for this particular power series? So let's start with the common ratio r. So as we know, this is in the form a times r to the n. So we could see that r is whatever is raised to the n power, or n plus 1 power. So this is r. So we know that the absolute value of r has to be less than 1, which means that x minus 1 within the absolute value symbol, that has to be less than 1. So this is in the form the absolute value of x minus c is less than r. So the radius of convergence for this problem is 1, r equals 1. Now to find the interval of convergence, we need to open the absolute value expression. So we can say that x minus 1 is less than 1, but greater than negative 1. And now add in 1 to both sides, or rather all three sides. X is less than 2, but greater than 0. Now one thing I want to mention is that the r value, which we know it's x minus 1, it's really based on this particular series, because that series is a geometric power series. This particular power series is no longer geometric due to the n plus 1 on the bottom. Nevertheless, the common ratio r is still the same, because if you look for it based on the original geometric power series, it's right here. And so these two expressions, x minus 1, will be the same if you integrate or differentiate it. So if you look for r in this expression, it's going to be the same. Now we need to check the endpoints to find the interval of convergence. So let's start with this power series. I had to clear the board because there was just too much stuff on it. So let's start with 0. What we need to do is plug in 0 into the series. So when x is 0, we're going to have negative 1 to the n power, 0 minus 1, which is negative 1, and that's going to be to the n plus 1 power over n plus 1. So we're going to have negative 1, n plus 1, that's 2n plus 1. And let's divide that by n plus 1. So what type of series do we now have? Is this an alternating series? Negative 1 to the 2n plus 1, that's basically negative 1 to the 2n times negative 1 to the 1. And notice that for all n values, negative 1 to the 2n will always be even. You can write that as negative 1 squared raised to the n power. And negative 1 squared is 1. And 1 to the n is just 1. Anything raised to the 1 raised to anything is 1. So this whole thing is just negative 1. At this point, we now have negative 1 over n plus 1. So will the series converge or will it diverge? To find out, let's use the integral test. So we're going to integrate the corresponding function from 1 to infinity of negative 1 over x plus 1. And the antiderivative of that, it's going to be the natural log of x plus 1 with a negative sign in front of it. And this is an improper integral, so we need to use limits to express it. So we're going to have the limit as b goes to infinity of negative natural log b plus 1 minus ln of 2. So as b goes to infinity, what happens to the natural log of b plus 1? That's going to go to infinity as well. So we're going to have negative infinity minus some constant, which is negative infinity. So therefore, if the integral diverges, then the series diverges as well. So 0 is not included in the interval of convergence. So we can write it like this. This is going to be 0 to 2, and now we need to check the other endpoint 2. So let's plug in 2 into this expression. So this is going to be negative 1 to the n, and then 2 minus 1 is 1. 1 raised to the n plus 1 is just 1. So we now have this. This is an alternating series due to the negative 1 to the n. So the sign is going to be alternating. For the alternating series test, we need to show that it's going to pass the divergence test. So our a sub n is everything except the alternating part. So our a sub n is going to be 1 over n plus 1. As n goes to infinity, 1 over n plus 1 goes to 0. So that's the first part of the alternating series test. The second thing that we need to do is show that a sub n is a decrease in sequence. So a sub n is 1 over n plus 1. And a sub n plus 1, that's going to be 1 over n plus 2. So 1 over n plus 1 is always larger than 1 over n plus 2. So we have a decrease in sequence. Therefore, by the alternating series test, this series converges. So at 2, the series will converge. So we're going to include 2. So the interval of convergence is from 0 to 2, and the series is centered at c equal 1. And we know that the radius of convergence is 1. So that's it for this problem. Now let's try another example. In this case, we're going to work on arctangent of x. Now, what is the derivative of arctangent of x? If you recall, it's 1 over 1 plus x squared. So therefore, we could say that the integral of 1 over 1 plus x squared dx is arctangent of x plus c. So let's find a power series representation of this expression. So let's change the positive sign into a negative one. So 1 plus x squared is going to be 1 minus negative x squared. And so now it's in the appropriate form. So we can see that a is equal to 1, and the common ratio r is negative x squared. So using the geometric series in this form, we can write it like this. It's going to be 1 times negative x squared to the n. And negative x squared, that's negative 1 times x squared. And both of these are raised to the n. And x squared raised to the n, we can write that as x to the 2n. So this particular series corresponds to 1 over 1 plus x squared. So now let's take this series and let's put it into that expression. So we now have the integral of this series of negative 1 to the n, x to the 2n, from 0 to infinity, and that's equal to arctangent of x plus the constant of integration. Now go ahead and integrate the left side of the equation. So we're going to have this series from 0 to infinity, and negative 1 to the n, that's a constant, so let's rewrite that. And let's use the power rule for integration on x to the 2n. So we need to add 1 to the exponent and then divide by that result. Now the next thing we need to do is determine the value of c, the constant of integration. So what value for x should we plug in? Let's plug in 0, because as we can see, it's centered at 0. 0 to the 2n plus 1, that's going to be 0. So this entire left side will be 0 when x is 0. and that's going to equal arctangent of 0, which is 0, plus c. So 0 is equal to c. So therefore, this is the power series for arctangent of x. This is the answer. Now let's write out a few terms in a sequence. So when n is 0, we're going to get x, or x to the 1 divided by 1. Because 2n plus 1 is equal to 1 when n is 0. When n is 1, negative 1 to the first power, that's going to be negative. And 2n plus 1 becomes 3. So this is going to be x to the third power divided by 3. And then if we continue the pattern, it's going to look like this. So that's the power series for arctangent of x. Now let's talk about the interval of convergence and the radius of convergence. So what is the common ratio r? If you look at this particular series, it's not immediately evident. It's not x. Well, at least not technically. If you recall, this particular series was based on the original geometric series, or geometric power series, of negative x squared to the n. And earlier in this problem, we defined r to be negative x squared. So that's really what it is. You could see it though in this expression. You have to look at everything that's raised to the n power. So you could see that x squared is raised to the n power, and negative 1 is raised to the n power. Thus r is technically negative x squared. Now, for the original geometric series, it's going to converge when the absolute value of r is less than 1, which means that the absolute value of negative x squared has to be less than 1. Negative x squared and positive x squared, when you take the absolute value of it, the results are the same. So thus we have this. And now if we take the square root of both sides, we could say that the absolute value of x is less than 1. So therefore, the radius of convergence is 1. And then we can rewrite this expression as x is less than 1, but greater than negative 1. This is the interval of convergence for the original geometric power series. Now, when you integrate or differentiate it, the endpoints of the interval of convergence may or may not change. So for the original geometric series, that is the geometric power series, the interval of convergence is negative 1 to 1. It does not include 1 because for a geometric power series, it can only converge when r is less than 1, not equal to 1. However, when we integrate or differentiate the geometric power series, that can change. So it's still going to be in this range, but this time it may or may not include negative 1 and 1. That's what we need to check for. So let's go ahead and do that. So if we replace x with 1, what's going to happen? So we're going to get this series, negative 1 to the n, and then 1 raised to the 2n plus 1. That's just 1. And 1 times anything is itself, so that will just disappear. And we're going to get this. Now notice that this series converges by the alternating series test. So if we take the limit as n goes to infinity for 1 over 2n plus 1, that's going to be 0. And we can also say that 1 over 2n plus 1 is greater than or equal to 1 over 2n plus 1 plus 1. So therefore, we have a decrease in sequence. So by the alternating series test, this particular series converges, which means that positive 1 is included. So we have negative 1 to 1, but a bracket at 1. Now let's check it for this example. So let's plug in -1. So we're going to have -1 to the n times -1 to the 2n plus 1 divided by 2n plus 1. So let's see if we can simplify what we have here. So this becomes -1 to the n and -1 to the 2n plus 1. Let's write it as -1 to the 2n times -1 to the 1. Now these two I'm going to combine into a single expression. So that's going to be -1 to the n plus 1. And -1 to the 2n, that's -1 squared raised to the n. And -1 squared is +1. So we have 1 to the n times what we have here, which is 1. So all of this reduces to -1 to the n plus 1. So this becomes -1 to the n plus 1 over 2n plus 1. And this is still an alternating series, just like what we had when x was +1. So you can follow the same steps. You can take the limit as n goes to infinity of 1 over 2n plus 1. So that's going to be 0. And you could say that a sub n is greater than or equal to the next term, a sub n plus 1. And so 1 over 2n plus 1, that's going to be greater than or equal to 1 over 2n plus 1 plus 1, which becomes 2n plus 3. So by the alternating series test, it converges when x is equal to -1. Now we said that the radius of convergence is 1, and this particular series is centered at 0. 0 is the midpoint between -1 and 1. And so that's it for this particular problem. So now you know what the power series is for arctangent of x. And you know the radius of convergence and the interval of convergence.